Okay, next we have tangent planes in linear approximations video 2. So the last thing we need to talk about is differentials, which are kind of a weird little topic. We're going to make sense of them in 2D first. So the whole idea is we have this function here, and we have a point on the function where we could draw in our tangent line. Okay, and then we're going to move to a point further down the line. Oops, I want to make that a little bit farther in though. Just a second. My drawings are being a little glitchy, so I might have to go a little bit slow and be patient here. Okay. Okay, so maybe a point right here. Okay, and then on our axis, okay, that point is at A, and then we have, let's see, f of A. Okay, and then that would also be, we're going to call anything on the function f of whatever, and anything on the line y of whatever. So that would also be y of A, right? They're at the same spot there, okay? But then we get a little bit further down here, and we have A plus delta x, okay? And on our line, our y value would be y of A plus delta x. But on our curve, I'm going to use a different color here. I'm going to use the lighter green to go with the lighter blue on the curve, okay? That would be f of A plus delta x. Oops, left out my delta. This has been really glitchy. Okay. Come on. Okay. So again, that tangent line would be at the point A, f of A, and it would have the slope f prime of A. Okay. So we could come up with the equation of that tangent line, right? It would be y minus whatever f of A is equals f prime of A times x minus whatever A is. Or we could rearrange it, y equals f of A plus f prime of A x minus A. Okay. Now we're going to label a couple things on here. So the first thing we're going to label is if we take a look at moving along the curve. So this would be a distance of delta x. Okay. And from the curve, I probably should use my light green there. Okay, this distance is delta y. Okay, now if we look at the line, it's the same delta x. We're going to call that dx. And then we're going to call that distance here dy. Okay, so delta x and delta y are measured to the curve. And then dx and dy are measured on the line. Okay, so we can see here that obviously delta x equals dx. Okay, dy is what we call the differential. Okay, so that's kind of your big term here. Dy is the differential. A couple things too, you can tell here that dy over dx that would be the slope of the tangent line, so that's f prime of x, okay? And we can rewrite that as dy, your differential, is f prime of x dx, okay? So it's basically, if you make any move in the x direction, how much are you going to move in the y direction on that line? Okay, that's all the differential is. So now we're going to plop that over into 3D. Make a nice big graph here. This is where it's going to get a little bit iffy on the drawing here. So I'm going to do the best I can. Okay, if we have a surface, so let me draw in. So like kind of a curved surface here. Okay, so we have the surface, z equals f of xy. Okay, then let's do a point on this. Let's do a point right here. Okay, so let's say A, B. Okay, so we would have right here the point A, B, f of A, B. Okay. And then let's say that we have the tangent plane at that point. Okay, so I'm going to try to draw that. Maybe do use kind of a lighter color here. So let's think about what would be going on right at that point. Maybe we've got a tangent plane that looks like that. Okay, so think about if that blue curve was maybe like coming back up, and it was just, remember we use that term like it just kisses the plane there. Okay, so it's not going through the plane. So we're going to have a tangent plane, z equals f of AB plus differential at AB, x minus a, plus the differential in y, not differential, partial, in y at AB of y minus b. Okay, so that's the equation of your tangent plane. All right. Now, let's say that we go down a distance to get to, let's go to that upper corner here. Okay. So let me get that down here. Okay, so then we're going to have delta x, and we'd have a plus delta x. And then we'd have delta y, so we'd have b plus delta y. And then way up here, let's scroll down a little bit here. Getting glitchy, come on. Okay, so let's say that that point would be a plus delta x, b plus delta y, f of a plus delta x, b plus delta y, which would also be f of a b plus delta z. If you want to think about it that way, right? They're changing the z direction. Okay, so we can even think about, let's see here. How do I want to do this? I'm just going to kind of do a delta z kind of off to the side here. Okay. So it's the difference in heights of those 2 points. Okay. So we would again measure our delta x, delta y, and delta z on the curve. Okay, so those are differences taken to the curve. And then we would have our dx, dy, and dz on the plane. Okay, and just like in 2D, delta x will equal dx, and delta y will equal dz. Okay, so in our x direction, we're moving from this green point. Oh, you know what? I made the purple point. I feel like I'm looking at it backwards now. It's okay. Did I make kind of like a weird optical illusion? I think I did, but I didn't intend to make it kind of weird, but that's okay. The main thing here is that your plane has a different delta z, right? Like if you look, your plane would have like a dz here. Okay, that's being glitchy. All right, but then all the way up to the point would be delta z. Okay, so that's your differential there, is that dz. Okay, so again, a lot of weird drawings and talking here, but we're gonna get the basics out of here. Dz is going to be dz dx. Notice those are partials times dx. Okay, so along that plane, wait for it to show up, we're thinking about that partial in x. So we're thinking about we're moving in the x direction, okay, and then we're going to move up z according to that partial derivative. And then we're going to take our step in the y direction and take that second step, okay, and that will get our total change in z. Okay, again, think of about a slope times the distance in the x direction plus a slope times the distance in the y direction. That's going to get our ultimate change in z. We can also write this. Okay, and then if your plane is doing a good approximation, then your f of xy will be approximately f of ab plus that dz. Okay, that little change in the z direction. Okay, that's what you're doing with your linear approximation. You're starting at a point and moving up the z direction using a plane to estimate what's actually going on the curve. Okay, let's get a nice example here. I like drawing, but sometimes it's hard to not be in the same room and try to explain a drawing like that to you guys. But anyways, here's our example. We've got z equals f of xy, which is x squared plus 3xy minus y squared. Okay. So we're going to find our differential. Okay, so dz is partial in z, or partial in x times dx. And then plus partial in y dy. Okay, and then we can use that to make some approximations. So first of all, partial in z over partial in x is 2x plus 3y. Partial in y is 3x minus 2y. So our differential is 2x plus 3y dx plus 3x minus 2y dy. Okay, so now what we can do here is we can use, instead of finding the equation of the tangent plane, we can just use our differential here. Okay, so let's say that x goes from 2 to 2.05 and y goes from 3 to 2.96, and we find delta z and dz. Okay, so now remember, delta z is the difference between what we see on is the difference between the two values, okay? And then dz would be the difference if we use the linear approximation, okay? All right, so dz, we're going to do that first, would be 2 times x, because we're starting, this is where we start, okay? So 2 times 2 plus 3 times 3. And then our change in x, our dx is 0.05. Okay, and then 3 times 2 minus 2 times 3. And then our change in y is negative 0.04. Okay, so if we simplify that all out, let's see here. I'm just going to jump ahead. We get, since it's being so glitchy, dz is 0.65. Okay, again, if I scroll back up, remember dz is measured on the plane. Okay, so dz would be like my tangent plane approximation. Okay, using the approximation at the point 2,3 to approximate what's going on at 2.05, 2.96. That differential will be the difference between the two. Okay, so whatever, in other words, it keeps getting all glitchy on me. Okay, I want to go back up to, hopefully this is almost done here. Okay, so f of 2.05, 2.96 is approximately f of 2.3 plus 0.65. Okay, so I could find f of 2.3 and add 0.65 to it. Okay, now delta z is on the curve. So that's just f of 2.05, 2.96 minus f of 2.3. Okay, and that is 0.6449. Okay, so if I were to find f of 2.3, I'm sorry, 2.3, and add 0.6449 to it, I get the actual value of f of 2.05, 2.96. Okay, if I were to get f of 2.3 and add, it's so glitchy, and add my differential to it, 0.65, I'll get an approximation. I'm sorry, you guys, it's not scrolling well here. Okay, let me get this, go back up there. Okay, and now. Oh my gosh, okay, go back up there. All right, and that will give me approximately, we are almost done, I hope, f of 2.05, 2.96. Okay, so your differential is really just, how much you add on from where you're beginning to get to your approximation. Okay, it's just another way of looking at it. All right, so I apologize for the glitchiness. I'm just gonna make sure we understand here that this is f of a b plus delta z equals f of a plus delta x, b plus delta y. And this is f of a b plus dz is approximately equal to f of a plus delta x, b plus delta y. And keep in mind, dx is delta x and dy is delta y. Okay. Oh shoot, I forgot. There's one last example, so I'm not quite done yet. An example of when you're going to use differentials, so they're not going to come up that much, but they give you like a maximum error. So the example in the book is, say we have the base of a cone, right circular cone, has a measured radius of 10 centimeters and height 25 centimeters. Okay, measurement error would be as much as 0.1 centimeter in each measurement. Okay, I apologize for the handwriting here. It's the program. Okay, find the max, oh, now we're good, error in volume. Okay, so let me change colors here. Volume of a cone is 1/3 pi r squared h. Okay, now the max error would be your differential in V, so dV. Okay, so we need to do our partial with respect to r times the change in r. So we're just swapping out variables. Instead of x, y, and z, we are using r, h, and v. And then the partial in h times dh. Okay, your partial in r would be 2/3 pi rh, and then dr. And then your partial in h would be 1/3 pi r squared, and then we're going to have dh. Okay, so now we can just plug in our values with r being 10, h being 25. And then dr, right, the differential in the r direction, the differential in the h direction, that's the error. So 0.1 plus 1/3 pi 10 squared, also times 0.1. Okay, so let's see here. We get 250 times 2 would be 500 times 0.1 is 50 pi over 3. Plus 100 times 0.1 would be 10, so 10/3 pi. That should be a plus. And so then we get 60 pi over 3, or 20 pi. And that would be, we're doing volume, so it'd be centimeters cubed. Okay, so again, if those are our measurements, we know our instrument could be off by as much as a millimeter, right, 0.1 centimeters. Our volume could be off by as much as 20 pi centimeters cubed. Okay. Then the very last thing, they always go into this at the end, is if there's more than 3 variables. So you have f of x, y, z, dot, 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 okay, equals f of a, b, c, dot, 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 plus all of your partials. Right? So it's just take the formula and apply it with more variables. Okay. And we could write that with some different notations there. Okay, so delta, maybe w, f of x plus delta x, y plus delta y, z plus delta z, whatever, minus f of x, y, z, right? Because that delta is always measured on the curve, okay? And then your differential, how much your approximation differs by. Partial in z with respect to x dx. Partial in z with respect to y dy. Oh, that shouldn't be z, that should be w. A mistake in my notes. It's coming. Hold on. Okay. Okay. So it's just, you can do it in more than one variable. You just follow the same pattern. Okay. I apologize for the glitchiness, but hope you got the basics there. We'll see you guys next time.